go in this lecture and answer two questions. In the first question, we find out the area of this green shape using two different methods. And in the second question, we will find out the area of this circle that intersects with this right triangle ACP at those 2 points. So we start with the first question. In the following, we have quarter circle AOB. We know that this is side OB. This equals to 2 units in its length. This is line segment AD. This equals to line segment DO in its length. Again, our task is to find out the area of this green shape. The green shape, it's actually the right green triangle DCB. So we have to find out the area of this green right triangle DCB. So first of all, AOB is a quarter circle, and therefore this is angle AOB. This is the right angle. In addition, OB and OA, they are both the area of the quarter circle. The radius OB equals to 2, and therefore the radius OA must be also equal to 2 units in its length. The radius AO, that equals to 2, has been bisected at this point D. That is to say, it is divided at point D in 2 halves. The first half is AD and the second half is DO. The length of the radius is 2, and therefore each half must be equal to 2 over 2, that is 1. So the first half AD equals to 1 units in its length, and the second half of the radius AO must be also equal to 1 unit in its length. Point D is the midpoint of the radius AO. So each half must be equal to 1. So in the next step, we will implement the Pythagoras theorem on this right triangle DOB. And again, we will implement the Pythagoras theorem on this right triangle DOB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle DOB, here by PT is a ratio from Pythagoras theorem. So in this right triangle DOB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to OD squared plus OB squared. And again, in this right triangle DOB, according to the Pythagoras theorem, the following equation is for dB squared, that is the square of the hypotenuse, equals to OD squared plus OB squared. dB is the missing hypotenuse, so we leave it as it is, so it is dB squared equals to OD squared. OD is 1, therefore OD squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So in total, we should find out that dB squared equals to 1 plus 4, that is 5. So dB squared equals to 5. Here we take out of this equation and find again that the length of the hypotenuse dB is equal to the square root of 5 units. This is the hypotenuse dB that equals to the square root of 5 units in its length. In the next step, we will complete this quarter circle to a circle. completed the quarter circle to a circle, and then we will extend the radius BO by straight line until it touches the circle. And we define the touching point of the extended radius BO with this circle. This point is point P. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. This is equals to 2 units in its turn. BO is the radius of this circle, so BO is a radius, it is absolutely a straight line. When we extend the straight line BO by a straight line, the result BP must be also a straight line. So BP is a straight line. BP is a straight line that touches the circle at those 2 points, B and P, and therefore BP is a chord. BP is a chord that passes through point O, that is the center of the circle, and we know then, that any chord that passes through the center of the circle must be the diameter of the circle. And therefore BP is the diameter of the circle. So, what is on? BP is the diameter of this circle. In the next step, we will extend the radius AO by straight line until it touches the circle. And we define the touching point of the extended radius AO with this circle. This point is point Q. For the same reason that PB is the diameter of the circle, AQ must be also the diameter of the circle, because AO is the radius. We extended the radius AO by straight line, and the result AQ must be the diameter of the circle. So, if you found out that chord AQ is the diameter of the circle, point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. This goes to 2 units in its name. So in total, we found out that PB and AQ are both the diameter of this circle. So in the next step, we extend the radius. We extend side CD of this outside DCB by straight line until it touches the circle. But the question is where the extended side CD will touch the circle. We will assume that the extended side CD, the extended side CD will touch the circle at this point, point N. So according to our assumption, we have here triangle ACN. Again, this is triangle BCN. Again, this is triangle BCN. According to what is given as the equation, triangle BCN is a right angle, it is equal to 90 degrees inside. Triangle BCN is subset of this chord BN. Chord BN is definitely not the diameter of the circle. Why chord BN is not the diameter of the circle? Because of the fact that chord BN doesn't pass through point O, that is the center of the circle. And we know that any chord that doesn't pass through the center of the circle cannot be the diameter. So, in conclusion, we found out that according to our assumption that the extended side CD will touch the circle at point N, we have here triangle BCN equals to 90 degrees in size according to what is given to the equation. And still, triangle BCN doesn't subset on the diameter of the circle because of the fact that triangle BCN subset on chord BN, that is not the diameter of the circle. So it is a contradiction to rule 5. I repeat quickly on rule 5. according to rule 5, any peripheral angle that is equal to 90 degrees inside must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAN that is equal to 90 degrees inside. And therefore, according to this rule 5, peripheral angle MAN must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on chord MN, that is the diameter of the circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees inside must subtend on the diameter of the circle. But here, now what you are knowing, we have peripheral angle BCN is equal to 90 degrees inside, and it doesn't subtend on the diameter of the circle because chord BN is definitely not the diameter of the circle. So due to the contradiction to rule 5, we conclude that the extended side CD will not touch the circle at point N. In the next step, we assume that the extended side CD will touch the circle at this point M. So according to our assumption, we have here peripheral angle BCM. This is peripheral angle BCM. It is equal to 90 degrees inside according to what is given to the question, and peripheral angle BCM subset of chord BM. Chord BM is definitely not the diameter of the circle because of the fact that chord BM doesn't pass through point O, that is the center of the circle. So again, we have contradiction to rule 5 because of the fact that peripheral angle BCM that is equal to 90 degrees inside must subtend on the diameter of the circle, but peripheral angle BCM subtend on chord BM that is definitely not the diameter of the circle. So due to the contradiction to rule 5, we conclude that the extended side CD will not touch the circle at point M. And therefore, we have to conclude that the extended side CD will touch the circle at point P and not in any other point. Now, we don't have contradiction to rule 5 anymore. Why? Because we have here peripheral angle BCM that is equal to 90 degrees in size. Peripheral angle BCM subtend on chord PB, that is the diameter of the circle, exactly according to rule 5. Okay, so here we have triangle PDO. What is the size of this angle? Actually, PB is the diameter of the circle, so PB is the diameter of a circle, it is absolutely a straight line. So if you focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line PB at point O? We have this angle that is a right angle, plus this missing angle, and total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. This is the right triangle PDO. PO equals to 2, DO equals to 1, and we only found out that any right triangle that has two sides with 2 and 1, the opposite must be equal to the square root of 5. And the opposite of this right triangle POD must be equal to the square root of 5 units in itself. Actually, those two triangles can go into each other according to side angle side rule, and therefore they must have also the same hypotenuses. The hypotenuse DB equals to the square root of 5, and therefore the hypotenuse DP of this right triangle PDO must be also equal to the square root of 5 units in its length. in the next step, we will implement all 24 in our drawing. So repeat quickly on all 24. All 24 is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So all 24 is true for any chords that intersect with each other inside the circle. So in the moment we have a circle, this is called AB, that intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 24 in our drawing. Well, in our drawing, chord AQ, AQ is the diameter of the circle, that is the biggest chord in the circle. Chord AQ intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. First of all, why CP is a chord? Because of the fact that we extended side CD, that is one side of this 100 dB. So CD is the side of a triangle, it is absolutely a side line. When you extend the side line by side line, the result CP must be also a side line. But CP is a side line that touches the circle at those 2 points C and P, therefore CP is a chord. So here, so I mentioned before, we can implement all 24. Why? Because we have chord AQ that intersects with chord CP at point D. So all the requirements for full 24 are satisfied, and therefore we can implement here all 24. So until now. Chord AQ intersects with chord CP at point D. Repeat again. Chord AQ intersects with chord CP at point D. So all the requirements for full 24 are satisfied, and therefore we can implement here all 24. According to all 24, the following equation is true. AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. So, until now, according to all 24, the following equation is true. AD times DQ equals to CD times DP. And again, according to all 24, the following equation is true. AD times DQ equals to CD times DP. AD is 1. Times DQ, DQ in total equals to 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so leave it as it is. So it is CD times DP. DP is equal to the square root of 5 units in Islam. In total, according to all 24, actually found out that 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to square root of 5 times CD. Here we divide the equation by square root of 5. And finally we get that the missing side CD is equal to 3 over square root of 5 units in its length. This is the missing side CD. This is equal to 3 over square root of 5 units in its length. In the next step, we will implement the Pythagoras theorem on this green triangle DCB. We are looking for the area of this green triangle DCB, so we'll find out the missing side CB of this green triangle DCB by implementing the Pythagoras theorem on this green triangle DCB. Here by PT is abbreviation for Pythagoras theorem. So in this triangle DCB, dB squared, that is the square of the hypotenuse, equals to dc squared plus cb squared. And again, in this main triangle DCB, according to the Pythagoras theorem, the following equation is true. dB squared, that is the square of the hypotenuse, equals to dc squared plus cb squared. dB equals to the square root of 5, therefore dB squared is square root of 5 squared, that is 5. And it is equals to dc squared. dc equals to 3 over square root of 5, and therefore dc squared equals to 3 over square root of 5 squared, it's actually 9/5. Plus cb squared. cb is the missing side, so we'll leave it as it is. So in total, we should found out that 5 equals to 9/5 plus cb squared. Here we will multiply 5 by 5 and then we will divide it by 5 in order to account for this number. 5 times 5 is 25 divided by 5. We multiply it by 5 and we divide it by 5 and then so we change nothing. 25 over 5 is 5. So 25 over 5 equals to 9/5 plus cb squared. Here we subtract 9/5 of this equation and find again that 25/5 minus 9/5 is 16/5 equals to cb squared. Here we take a root out of this equation and find again that there is inside cb is equal to the square root of 16, that is 4 over square root of 5. So if you found out the difference inside CB of the triangle DCB is equal to 4 over square root of 5 units in itself. This is the missing side CB that is equal to 4 over square root of 5 units in itself. Now it is very easy to find the area of this green shape. The area of this green shape, the green shape is actually the right triangle DCB. Because again, the area of this green shape is actually the area of the green triangle DCB. And the area of this green triangle DCB equals to the base DC times the height CB over 2. And again, the area of this green triangle DCB is equal to the base DC times the height CB over 2. DC, the base DC equals to 3 over square root of 5 units in its length times the height CB. The height CB equals to 4 over square root of 5 units in its length. Divided by 2. So in total, we have found out that the area that we are looking for this question is equal to the value of this expression. So what is the value of this expression? 3 times 4 is 12, square root of 5 over square root of 5 is 5 over 2. So in total, this expression equals to 12 over 5 over 2. Here we move 2 to the denominator, and get this expression in total equals to 12 over 5 times 2. That is to say, it equals to 12 over 5 times 2, that is 10. It equals to 12 times square units inside. 12 times is 1.2. So in total, if you want the area that we are looking for in this question, that is the area of this green shape is equal to 1.2 square units in size. So we finish with the first method. In the next step, I will present you how to find out the area of this green shape according to the second method. BO and AO, they are both the area of the quarter circle. So equals to 2. Radius AO equals to 2 units in its length. The radius AO has been bisected at point D into 2 halves. Each half must be equal to 2 over 2. That is to say, it is 1. So the first half of AO is 1. And the second half of the radius AO must be also equal to 1. AOB is a quarter circle, and therefore this is angle AOB, this is right angle. In the next step, we complete this quarter circle to a semicircle. And we will extend the radius of B by a straight line until it touches the semicircle. And we define the touching point of the extended radius BO with this semicircle. This point is point P. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle, of the semicircle, is equals to 2 units in its length. BP is the diameter of the semicircle, and that is on the same expression that we did in the first method. BP is the diameter of the semicircle. In the next step, we will extend side CD of this right triangle DCB by side line until it touches the semicircle. I want to explain to you that the extended side CD will touch the semicircle at point P and not in any other point due to the contradiction to rule 5. The extended side CD must touch the circle at point P and not in any other point. So now we don't have any contradiction to rule 5 anymore. Why? Because we have triangle BCP. This is equal to 90 degrees inside according to what is given us in the question. And triangle BCB subtend on cos PB, this is the diameter of the circle. Exactly according to rule 5 that says that any triangle is equal to 90 degrees inside must subtend on the diameter of the circle or semicircle. This is called PB, this is the diameter of this semicircle, according to what we already proved in the first method. This angle equals to 90 degrees inside according to what we already proved in the first method. It is true according to rule 3. So I'll not repeat on the same explanation. According to rule 3, the sum of the angles from one side of a side line is equal to 180 degrees, and therefore this missing angle must be equal to 90 degrees in its size. This is the right triangle POD. We already found out that the hypotenuse POD equals to the square root of 5 units in its length, according to the Pythagoras theorem. In the next step, we will define this angle. This is actually angle DPO as alpha. And we will focus on this right triangle PDO. On this right triangle PDO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in this big right triangle PCB, this angle equals to alpha, and therefore angle alpha is a common angle that belongs to both triangles. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule, it said that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see from the drawing that the small right triangle PDO is similar to the big right triangle PCB according to angle similarity rule. So why those two right triangles are similar to each other? First of all, this is an angle alpha. Angle alpha is a common angle that belongs to both triangles. Angle alpha definitely belongs to the small right triangle PDO, and angle alpha definitely belongs to the big right triangle PCB. Therefore, angle alpha is a common angle that belongs to both triangles. So you can write down that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees also, and therefore they are equal to each other. So if you found out that all the angles of this small right triangle PDO are corresponding equal to all the angles of this big right triangle PCB, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. If you found out that this is the small right triangle PDO, it is similar. This is the sign of similar to this big right angle PCB according to angle similarity rule. Repeat again, we should find out that the small right angle PDO is similar to the big right angle PCB according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PD of this small right angle PDO over side PB of this big right angle PCB is equal to side DO of this small right angle PDO over side CB of this big right angle PCB, and it is also equal to side PO of this small right angle PDO over side PC of this big right angle PCB. So write it down. PD over PB equals to DO over CB equals to PO over PC. Repeat again. From the fact that the right small triangle PDO is similar to this big right triangle PCB, we derive that the following relationship exists between their sides. We will derive that side PD of the small right triangle PDO over side PB of the big right triangle PBC is equal to side DO of the small right triangle PDO over side CB of the big right triangle PCB, and it is also equal to side P of the small right triangle PDO over side PC of the big right triangle PCB. PD equals to the square root of 5 units in its length over PB. PB in total equals to 2 plus 2, that is 1. It is the diameter of the semicircle. Again, PB in total equals to 2 plus 2, that is 4. It is the diameter of this semicircle. So PB equals to 4, and it is also equals to DO is 1 over CB. CB is the recent side, so we leave it as it is. And it is equals to PO. PO is 2 over PC. PC in total equals to the square root of 5 plus DC. So in total, we should find out that square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of this equation are equal to each other, so we will get the equation 1 from those two sides that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. Here we will cross multiply this equation 1, and finding out that according to this equation 1, 4 times 1 is 4, is equal to the square root of 5 times CB. So in total we should find out that 4 equals to the square root of 5 times CB. Here we will divide this equation 1 by square root of 5, and finding out that the missing sign CB and again sign PCB right triangle DCB is equal to 4 over square root of 5 units in its length. This is the missing side CB. This is equals to 4 over square root of 5 units in its length. Those two sides of this long equation are equal to each other. Therefore, we will create equation 2 from those two sides that are equal to each other. So according to equation 2, we get that square root of 5 over 4 equals to 2 over square root of 5 plus DC. So I write it down. So according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we cross multiply this equation 2, and we get that according to this equation 2, 4 times 2 is 8, so 8 equals to square root of 5 times square root of 5 plus DC. Okay, so in total according to equation 2, we found out that eight equals to the square root of 5 times square root of 5 plus DC. Here we will open the brackets on this side of this equation 2. We get according to this equation 2, 8 equals to the square root of 5 times square root of 5 is 5 plus square root of 5 times DC. Here we will subtract 5 from this equation 2. And we get that according to this equation 2, 8 minus 5 is 3, so 3 equals to the square root of 5 times DC. Here we will divide this equation 2 by square root of 5, and finally get that according to this equation 2, the missing side DC is equal to 3 over square root of 5 units in its length. This is the missing side DC, that is equals to 3 over square root of 5 units in its length. Now it is very easy to find out the area of this green shape. It is actually the area of this green right triangle DCB. Exactly as we did in the first method. The area of the green shape is actually the area of this green right triangle DCB. Okay, again, the area that we are looking for in this question, that is the area of the green shape, is actually the area of the green right triangle DCB. And the area of this green right triangle DCB equals to the base DC times the height CB over 2. And again, the area of this green right triangle DCB is equal to the base DC times the height CB over 2. The base DC equals to 3 over square root of 5 units in its length times the height CB is equal to 4 over square root of 5 units in its length. divided by 2. So in total, if you found out that the area of the green shape is equal to the value of this expression. Actually, I repeat on the solution from the first method. It's exactly the same. So I finish to solve this second method. So 3 times 4 is 12 over square root of 5 times square root of 5 is 5 divided by 2. Here we will move to the denominator and get that this expression in total equals to 12 over 5 times 2. So it is 12 over 5 times 2, that is 10. This is 12 terms. 12 terms is 1.2 square units in size. So if you found out that in both methods, that the area that we are looking for in this question, that is the area of this green shape, is equal to 1.2 square units in size. So we finished with the first question. In the next step, I present to the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle that intersects with this right line ACP at those 2 points. In addition, you know that this is line segment BC, this is equals to 1 unit in its length. This is line segment CP, this is equals to 4 units in its length. This is angle ACP, this is right angle, and the triangle ACP is right angle, of course. And in addition, this is the convex line point P. From this convex line point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. And please click on rule 2. According to rule 2, the lengths of 2 tangents from a convex line point to a circle are equal. In the drawing, we have a circle. This is the convex line point P. From this convex line point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, the length of tangent PA is equal to the length of tangent PB, or PA equals to PB. So we can actually implement rule 2 in our drawing. Well, because in our drawing, this is the convex line point P. From this convex line point P, we have 2 tangents to this circle. That is to say, tangent PA and tangent PB. And according to rule 2, they are equal to each other in their lengths. That is to say, PA equals to PB. So I write it down. And again, according to rule 2, I can found out that if you focus on the convex line point P, tangent PA equals to tangent PB in its length, according to rule 2. But it is given us a question that the length of this tangent PB in total is equal to 4 plus 1, that is 5. So you can write here that PB, tangent PB equals to 5 units in its length. And from this equation, PA equals to PB equals to 5. We derive that tangent PA must be also equal to 5 units in its length. So this is tangent PA, or tangent AP, is equals to 5 units in its length. In the next step, we will implement the Pythagoras theorem on this right triangle ACP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT, evaluation for Pythagoras theorem. So according to the Pythagoras theorem, this right triangle ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. This again according to the Pythagoras theorem, and this right triangle ACP, AP squared equals to AC squared plus CP squared. AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP equals to 5, and therefore AP squared is 5 squared, that is 25. And it is equals to AC squared. AC is the missing side, so we leave it as it is. This is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, it is 16. So in total, we should know that 25 equals to AC squared plus 16. Here we will subtract 16 from this equation. And get that 25 from 16 is 9 equals to AC squared. Here we take a root from this equation and get that the left of the missing side AC is equal to the square root of 9, that is 3. This is the missing side AC, that is equals to 3 units in its length. Yeah, AC equals to 3 units in its length, the missing side. BP is a tangent to this second point B. BP is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line BP at point C, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BP at point C? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we define the center of this circle. This point is point O. And we define the radius of this circle as x. Repeat again that point B is the point of tendency of tangent PB with this circle. In the next step, we will join points O and B together by a straight line. Point O is the center of this circle, point B is the point of the circle itself, and therefore OB is the radius of this circle. That is equals to x according to our definition. The radius of B that is equals to x. The radius of B is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. In the next step, we will do a construction. That is to say, from point O, that is the center of this circle, we will draw perpendicular on AC. Again, from point O, we will draw perpendicular on AC. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We define the touching point of the perpendicular from point O and AC. This point is point M. By doing this construction, we can do quadrangle OMCB. Inside quadrangle OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in size. So in quadrangle OMCB we have 4 right angles, and therefore quadrangle OMCB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OMCB, side BC must be equal to the opposite side OM. But BC is 1, therefore the opposite side OM must be also equal to 1 unit in its length. Likewise, according to the sum rule, in the sum rectangle OMCB, side OB must be equal to the opposite side MC. But OB is x, therefore the opposite side MC must be also equal to x units in its length. In the next step, we join points O and A together by straight line. Point O is the center of this circle, point A is the point of the circle itself, therefore OA is the radius of this circle, that is equals to x. In the next step, we will implement the Pythagoras theorem on this green right triangle, triangle OMA. Here by PT is evaluation for Pythagoras theorem. This right triangle OMA according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AM squared plus MO squared. And again, in this right triangle AMO, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AM squared plus MO squared. What is the length of this missing line 7, line 7 AM, or side AM? From the drawing, it is very easy to see that AM in total equals to AC on MC. So, write it down. AM equals to AC on MC. So AM in total equals to AC, that is 3, minus MC, that is x. So in total, AM equals to 3 minus x units in its length. And we only found out that according to the Pythagoras theorem, the right triangle OMA, AO squared, this is the square of the hypotenuse, equals to AM squared plus MO squared. The hypotenuse AO equals to x units in itself, and therefore AO squared is x squared. And it is equal to AM squared. AM is 3 minus x, and therefore AM squared is 3 minus x squared. Plus MO squared. MO is 1, therefore MO squared is 1 squared, this is 1. So in total, we have found out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of this equation, so x squared will get cancelled. After I cancelled x squared, in this side of the equation we left nothing, that is to say 0. While on the other side of the equation we have 9 plus 1, that is 10, minus x, minus 6x. So total we actually found out that the 0 equals to 10 minus 6x. Here we will add 6x to this equation and find out that 6x equals to 10. Here we will divide this equation by 2 and find out that 6x over 2 is 3x and it is equals to 10 over 2 is 5. So in total we should found out that 3x equals to 5. Here we will divide this equation by 3 and find out that the radius x of the circle is equal to 5/3. And again, we should find out that the radius of this circle, x equals to 5/3 units in itself. X equals to 5/3 units in itself. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, and therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 5/3, and therefore x squared must be equal to 5/3 squared. So in total, the area of our circle equals to pi times 5/3 squared. So it is pi times 5/3 squared. 5/3 squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we actually found out that the area of the circle is equal to either 25 pi over minus square units in size. In terms of numbers, this is equal to 8.73 square units in size. And again, we actually found out that the area that we are looking for in this question, that is the area of this circle, in total it is equal to either 25 pi over 9 square units in size, or in terms of numbers it is equal to 8.73 square units in size. So we finish with the second question. In the next step, I'll summarize the lecture. That is to say, we repeat on the solution of the first question with its solved methods, and then we repeat on the solution of this second question. Our task in the first question is to find out the area of this green shape. So in the drawing we have quarter circle AOB. OB equals to 2, AD equals to DO. This is angle DCB, that is a right triangle, and therefore triangle BCD is a right triangle. So we have to find out the area of this green right triangle BCD. The area of the green shape goes to the area of this green right triangle BCD. So we have to find out the area of this green right triangle BCD. So we start with the first method. In quarter circle AOB, this is angle AOB, this is right angle. This is in any quarter circle. In addition, we know that BO and OA, they are both the radius of the quarter circle, is equals to 2. So the radius AO must be also equal to 2 units in its length. At point D, the radius AO is intersected into two halves. Each half must be equal to the length of the radius over 2. That is to say, each half must be equal to the length of the radius is 2 over 2. So the first half of the radius AO equals to 2 over 2 is 1, and the second half, the O must be also equal to 1 unit in its length. The next step, we implemented the Bador's theorem on this right triangle DOB. According to the Bador's theorem, in any right triangle, the square of the opponent equals to the sum of the squares of the perpendiculars. In this right triangle DOB, dB squared, that is the square of the opponent, equals to DO squared plus OB squared. And again, in the right triangle DOB, according to the Bador's theorem, dB squared, that is the square of the opponent, equals to OD squared plus OB squared. dB is the missing side, so we notice it is, and it is equals to DO squared. DO is 1, therefore DO squared is 1 squared, that is 1, plus OB squared. OB is 2, therefore OB squared is 2 squared, that is 4. So in total, we have to find out that dB squared equals to 1 plus 4, that is 5. So dB squared equals to 5. Here we have to quote out the equation, find out that the missing hypotenuse dB is equal to the square root of 5 units in its length. This is the missing hypotenuse dB, that is equal to square root of 5 units in its length. In the next step, we completed this quarter circle to a circle. Then we extended the radius BO by sideline until it touches the circle. We define the touching point of the extended radius BO with this circle. This point is point P. PO is the radius of the semicircle or radius of the circle. So BO is a radius, it is absolutely a side line. When you extend the side line by side line, the result BP must be also a side line. So BP is a side line, but BP is a side line that touches the circle at those 2 points, P and B, therefore BP is a chord. BP is a chord that passes for point O, that is the center of the circle, and we know that any chord that passes for the center of the circle or semicircle must be equal to 90 degrees inside. Must be the diameter of the circle. So chord PB passes for point O, that is the center of the circle, and therefore it must be the diameter of the circle. So chord PB is the diameter of the circle. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle, equals to 2. Likewise, we extended the radius AO by side line until it touches the circle. We define the touching point of the extended radius AO with this circle. This point is point Q. So AQ is also the diameter of the circle because of the fact that PP is the diameter of the circle, AQ must be also the diameter of the circle because both of them are the radius of the circle that we extended by side line. If BP is the diameter of the circle, then AQ must be also the diameter of the circle for the same reasons. So in total, we found out that BP and AQ, they are both the diameters of the circle. So, and the point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle, this equals to 2. In the next step, we extended side CD of this right triangle BCD by side line until it touches the circle. But the question is where the extended side CD will touch the circle. We assume that the extended side CD will touch the circle at this point, point N. And therefore, according to our assumption, we have peripheral angle BCN that is equals to 90 degrees inside according to what is given as a question. and peripheral angle BCL subtend on chord BN. Again, peripheral angle BCL subtend on chord BN. Chord BN is definitely not the diameter of the circle because of the fact that chord BN doesn't pass through point O, that is the center of the circle, and because of the fact that chord BN is not doesn't pass through point O, that is the center of the circle, it cannot be the diameter of the circle. So we have here peripheral angle BCL, that is equal to 90 degrees inside, and still it doesn't subset on the diameter of the circle because of the fact that chord BN is not the diameter of the circle. And according to all 5, any peripheral angle is equal to 90 degrees inside must subtend on the diameter of the circle. So we have a contradiction to all 5. Due to the contradiction to all 5, the extended side CD will not touch the circle at point N. Then we assumed that the extended side CD will touch the circle at this point N. Therefore, according to our assumption, we have here peripheral angle BCM, that is equal to 90 degrees in size, according to what is given as a question, but still, peripheral angle BCM doesn't subtend on the diameter of the circle. Why? Because peripheral angle BCM subtend on chord BM, that is definitely not the diameter of the circle. Why chord BM is not the diameter of the circle? Because of the fact that chord BM doesn't pass through point O, that is the center of the circle. So we have again contradiction to all 5 because we have peripheral angle BCM that is equal to 90 degrees inside and still it doesn't subtend on the diameter of the circle. So due to the contradiction to all 5, we cancel the option that the extended side CD will touch the circle at this point N. Therefore, we must conclude that the extended side CD will touch the circle at point P and not in any other point. Otherwise, we have contradiction to all 5. Now, we don't have any contradiction to all 5 anymore because we have peripheral angle BCP that is equal to 90 degrees inside and it's subtend on chord BP, that is the diameter of the circle exactly according to all 5. So, conclusion, I shall find out that the extended side CD will touch the circle at point P and not in any other point. This angle equals to 90 degrees inside according to all 3. Because BP is a diameter, it is absolutely side line, so if you focus on the upper side of the side line BP at point O, here the sum of the angles must be equal to 180 degrees according to all 3. All 3 says that the sum of the angles on one side of the side line is equal to 180 degrees. So which angles we have at the upper side of the side line BP at point O, we have this angle, that is the right angle, plus this missing angle, in total the sum of those angles must be equal to 180 degrees according to all 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right angle PDO, PO equals to 2, DO equals to 1, and therefore the opponent's PD must be equal to the square root of 5 units in its length. Exactly like this triangle DOB. So the opponent's PD equals to the square root of 5 units in its length. So now we can implement all 24 in our drawing. We have implemented all 24 in our drawing. On page briefly on all 24, according to all 24, if chord AB intersects with chord CD at point O, then the following equation is true. AO times VO equals to CO times DO. So in the drawing, we have a circle, this is chord AB that intersects with chord CD at point O. In this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement all 24 in our drawing. In our drawing, this is called AQ. It is the diameter of the circle, and it is the biggest, the longest chord in the circle. Chord AQ intersects with chord CP at point D. Again, chord AQ intersects with chord CP at point D. Why CP is a chord? Because of the fact that CD is a side line. When you extend the side line by side line, the result CP must be also a side line. But CP is the side line that touches the circle at those 2 points, C and P. Therefore, CP is a chord. So, conclusion, we found out that chord AQ intersects with chord CP at point D. Again, chord AQ intersects with this chord CP at point D. So all the requirements of all 24 are satisfied, and therefore we can implement all 24. And again, we found out that chord AQ intersects with chord CP at point D. Therefore, according to rule 24, the following equation is true, that AD times DQ equals to CD times DP. Again, AD times DQ equals to CD times DP. And again, AD times DQ equals to CD times DP. AD is 1 times DQ. DQ in total is 1 plus 2, that is 3. And it is equals to CD. CD is the missing side, so we leave it as it is, times DP. DP equals to the square root of 5 units in its length. So in total, we found out that according to rule 24, 1 times 3 equals to CD times square root of 5. 1 times 3 is 3, so 3 equals to the square root of 5 times CD. Here we divide this equation by square root of 5, and finally found out that the missing side CD equals to 3 over square root of 5 units in its length. This is the missing side CD. This is equals to 3 over square root of 5 units in its length. The next step, implemented the paradox theorem on this green iron DCB. According to the paradox theorem, in this again time DCB, dB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. Repeat again, in this green iron DCB, according to the paradox theorem, the following equation is true. dB squared, that is the square of the hypotenuse, equals to DC squared plus CB squared. dB equals to the square root of 5, and therefore dB squared square root of 5 squared, that is 5, and it is equals to DC squared. DC is 3 over square root of 5, and therefore DC squared is 3 over square root of 5 squared, that is 9/5. Plus CB squared. CB is the missing side, so so it is CB squared. So we found out that 5 equals to 9/5 plus CB squared. Here we multiply 5 by 5, and then we divide it by 5 in order to come factor with this number. 5 times 5 is 25 over 5. So this expression equals to 25 over 5. And it is equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation, and we found out that 25/5 minus 9/5 is 16/5 equals to CB squared. Here we took out of those equations, and we found out that the missing side CB equals to the square root of 16, that is 4 over square root of 5. So CB equals to 4 over square root of 5 units in its length. This is the missing side CB, this is equals to 4 over square root of 5 units in its length. Again, our task is to find out the area of this green shape. The green shape is actually, it is the green iron DCB, so we have to find out the area of this green iron DCB. So again, the green shape, the area of the green shape is actually the area of the green iron DCB. So the area of this green iron DCB it is equals to the base DC times the height CB over 2. And again, the area of the green iron DCB in total it is equals to the base DC times the height CB over 2. This is 3 over square root of 5, CB is 4 over square root of 5 divided by 2. 3 times 4 is 12, square root of 5 times square root of 5 is 5 over 2. Here 12 over 5 over 2, we move 2 to the denominator here, and this expression in total equals to 12 over 5 times 2. So it is 12 over 5 times 2. 5 times 2 is 10. So in total, if you found out that the area of the green shape equals to 12 tenths, that is 1.2 square units in size. Again, if you found out that the area of this green shape is equal to 1.2 square units in size. So we finish with the first method. In the next step, I'll repeat on the solution of the second method of the first question. Here will be the quarter circle, therefore this is the right angle. BO and OA, the above the radius of the quarter circle is equals to 2. So the radius OA equals to 2. At point D, the radius OA is bisected into two halves. The first half must be equal to 2 over 2, that is 1. And the second half, the O must be equal to 1. In the next step, we completed the quarter circle to a semicircle. Then we extended the radius BO by side line until it touches the circle. We define the touching point of the extended radius BO with this semicircle. This point is point P. BO as a radius is absolutely side line. When we extend the side line by side line, the result PP must be also a straight line. So BP is a straight line that touches the semicircle at those 2 points, B and P, therefore BP is a chord. So BP is a chord that passes through point O, that is the center of the semicircle, and we know that any chord that passes through the center of the semicircle or a circle must be the diameter of the circle. Therefore BP is the diameter of the circle. This angle equals to 90 degrees according to all three. So I'm not repeating on the same explanation. In the right triangle PDO, the opposite PD must be equal to the square root of 5 units in its length, according to the Pythagoras theorem. I'm not repeating on the same explanation. And but before that, we actually extended the straight line CD by straight line until it touches the semicircle. In the first method, we only found out that the extended side CD must touch the circle or the semicircle at point P and not in any other point due to the contradiction to all 5. When the extended side CD touches the circle at point P, we don't have contradiction to all 5 anymore. One, because we have here prime angle BCP, that is right angle, and indeed in some sense on chord PP, that is the diameter of the semicircle, exactly according to all 5. That's that any prime angle that is equal to 90 degrees in size, like this prime angle, must subtend on the diameter of the circle or semicircle, and indeed prime angle BCP subtend on chord PB, that is the diameter of the semicircle, exactly according to all 5. Point O is the center of the semicircle, point P is the point of the semicircle itself, therefore P is the radius of the semicircle, that is equal to 2. So here we define this angle DPO as alpha, so in the right triangle DPO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle PCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this minus angle must be equal to 90 degrees minus alpha according to the sum of that said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that the small right triangle PDO is similar to the big right triangle PCB. So when those two right triangles are similar to each other. First of all, this is angle alpha, this is the common angle that belongs to both triangles. So we can write down that angle alpha equals to itself the common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if we found out that all the figures of this small right triangle PDO corresponding equal to all the figures of this big right triangle PCB, and therefore those two right triangles are similar to each other according to angle similarity rule. So if we found out that the small right triangle PDO is similar, this is the sign similar to the big right triangle PCB according to angle similarity rule. And so we found that the small right triangle PDO is similar to the big right triangle PCB. We derive that the following relationship exists between their sides. We derive that side PD of this small right triangle PDO or side PB of this big right triangle PCB is equal to side DO of this small right triangle PDO or side CB of this big right triangle PCB. And this also equals to side PO of this small right triangle POD or side PC of this big right triangle PCB. And again, for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PD of the small right triangle PDO over side PB of the big right triangle PCB equals to side DO of the small right triangle PDO over side CB of the big right triangle PCB over side PO of the small right triangle PDO over side PC of the big right triangle PCB. PD is equal to 5, PB is 4, DO is 1, CB is the missing side, so it is PO is 2, and PC in total equals to the square root of 5 plus DC. And again, PC in total equals to the square root of 5 plus DC. So in total, we found out that the square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. Those two sides of the equation are equal to each other, so we can have equation 1 from those two sides that are equal to each other. So according to equation 1, square root of 5 over 4 equals to 1 over CB. And again, according to equation 1, square root of 5 over 4 equals to 1 over CB. Here, of course, multiplying the equation, we can find out that 1 times 4 is 4 equals to square root of 5 times CB. Here, we divided the equation by square root of 5 and finally found out that the missing side CB equals to 4 over square root of 5 minutes instant. This is the missing side CB, this equals to 4 over square root of 5 minutes instant. Those two sides of this long equation are equal to each other, therefore we can get equation 2 from those two sides that are equal to each other. According to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Repeat again, according to equation 2, square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here, of course, multiply the equation, and we found out that 4 times 2 is 8, and it is equals to the square root of 5 times square root of 5 plus DC. And again, according to equation 2, we found out that 8 equals to the square root of 5 times square root of 5 plus DC. We open the box of this expression and we found out that 8 equals to square root of 5 times square root of 5 is 5, and the square root of 5 times DC is square root of 5 DC. So in total, we found out that 8 equals to 5 plus square root of 5 times DC. Here we subtract 5 from this equation, and we found out that 8 times 5 is 3 equals to the square root of 5 times DC. Here we divided this equation 2 by square root of 5, and finally we found out that the missing side DC equals to 3 over square root of 5 minutes instant. This is the missing side DC, is equals to 3 over square root of 5 minutes instant. Our test is to find out the area of this green shape. The green shape is actually the right green triangle DCB. And again, our test is to find out the area of the green shape, and the green shape is actually the right green triangle DCB. The area of this green right triangle DCB equals to the base DC times the height CB over 2. But again, the area of the green right triangle DCB in total it is equals to the base DC times the height CB over 2. DC is 3 over square root of 5 times CB is 4 over square root of 5 divided by 2. 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. Here we move 2 to the denominator, so this expression in total equals to 12 over 2 times 5. 2 times 5 is 10, so this expression equals to 12 tenths, that is 1.2 square root in size. So in total, we found out in both methods that the area of this green shape is equal to 1.2 square root in size. So finish to repeat on the first question. In the next step, I repeat on the solution of the second question. In the second question, our task is to find out the area of this circle. So in the drawing, we have a circle that intersects with this right triangle ACP at those 2 points. Line 7BC equals to 1 unit in length, line 7CP equals to 4 units in length, line 7CP equals to 4 units in length. This is the common sum point, point P. From this common sum point, point P, we have 2 tangents to the circle, tangent PA and tangent PB. And according to all 2, they are equal to each other. So repeat quickly on all 2. According to all 2, the lengths of 2 tangents from a common sum point to a circle are equal. In the drawing, we have a circle. This is the common sum point, point P. From this common sum point, point P, we have 2 tangents to the circle, tangent PA and tangent PB. And according to all 2, they are equal to each other in their lengths. That is to say, tangent PA equals to tangent PB in its length, or PA equals to PB. So we can actually implement all 2 in our drawing. Why? Because in our drawing, this is the common sum point, point P. From this common sum point, point P, we have 2 tangents to this circle, tangent PA and tangent PB. And according to all 2, they are equal to each other. This is to say PA equals to PB. So if we focus on the common sum point, point P, from the common sum point, point P, we have 2 tangents to the circle, tangent PA and tangent PB. And according to all 2, they are equal to each other. This is to say PA equals to PB. But it is given as a question that the length of this tangent PB in total equals to 4 plus 1, that is 5. So we can write here that the left tangent PB equals to 5, and from this equation PA equals to PB equals to 5, we will learn that PA also equals to 5 units in its length. This is tangent PA is equals to 5 units in its length. In the next step, we implement the Pados theorem on this right line ACP. According to the Pados theorem, in this right line ACP, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. And again, the right line ACP, according to the Pados theorem, AP squared, that is the square of the hypotenuse, equals to AC squared plus CP squared. AP is 5, and therefore AP squared is 5 squared, that is 25, and it is equals to AC squared. AC is the missing side, so related to this, so it is AC squared plus CP squared. CP is 4, therefore CP squared is 4 squared, that is 16. So in total, we found out that 25 equals to AC squared plus 16. Here we subtract 16 from this equation, and we found out that AC squared equals to 25 minus 16, that is 9. So AC squared equals to 9. Here we took out all those equations, and we found out that the missing side AC equals to the square root of 9, that is 3. This is the missing side AC of this right line ACP, and it is equals to 4 units in its length. In the next step, we define the center of this circle, this point. We define the center of this circle, this point O. We define the radius of this circle as x. And then we join points O and B together by side line. Point O is the center of the circle, point B is the point on the circle itself, so OB is the radius of the circle, that is equals to x according to our definition. The radius OB is equals to x, the radius OB is drawn to point B, that is the point of tendency PB with this circle. And whenever your radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. PB is a tangent to the circle, so PB is a tangent, it is absolutely a straight line. So if you focus on the upper side of the straight line BP at point C, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have in the upper side of the straight line BP at point C? We have this angle equal to 90 degrees inside, plus this missing angle, in total the sum of those angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in size. In the next step we did the construction, that is to say from point O, that is the center of this circle, we draw perpendicular on AC. Again from point O, we draw perpendicular on AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and AC, this point is point M. When doing this construction, we can do the quadrilateral OMCB. In quadrilateral OMCB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this 4 pieces angle, in total must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral OMCB we have 4 right angles, and therefore quadrilateral OMCB is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So rectangle OMCB, side CB must be equal to the opposite side OM. But CB is 1, therefore the opposite side OM must be also equal to 1 unit in itself. Likewise, according to the sum rule, in the sum rectangle OMCB, side OB must be equal to the opposite side MC. But OB is x, therefore the opposite side MC must be also equal to x units in itself. What is the length of this missing line segment AM? AM equals to AC minus MC. Again, AM equals to AC minus MC. So AM equals to AC, that is 3, minus MC, that is x. So in total, AM equals to 3 minus x units in its length. In the next step, we join points O and A together by side line. Point O is the center of the circle, point A is the point of the circle itself, and therefore OA is the radius of the circle, is equals to x. In the next step, we implemented the Pados theorem on this green right line OAM. According to the Pados theorem, in this right line OAM, OA squared, that is the square of the hypotenuse, equals to AM squared plus MO squared. Again, in this green right line OMA, according to the Pados theorem, the following equation is true. OA squared, that is the square of the hypotenuse, equals to AM squared plus OM squared. OA is x, therefore OA squared is x squared, and it is equals to AM squared. AM is 3 minus x, therefore AM squared is 3 minus x squared, plus OM squared. OM is 1, so OM squared is 1 squared, that is 1. So in total, we should find out that x squared equals to 3 minus x squared plus 1. So x squared equals to 3 minus x squared. 3 minus x squared equals to 3 squared, that is 9, plus x squared, minus 2 times 3 times x, that is minus 6x plus 1. Here we have x squared on both sides of the equation, so x squared will get cancelled. After cancel x squared on this side of the equation, we have nothing, that is to say 0. And on the other side of the equation, we have 9 plus 1, that is 10, minus 6x. So in total, we found out that 0 equals to 10 minus 6x. Here we added 6x to this equation, and found out that 6x equals to 10. Here we divided this equation by 2, and found out that 6x over 2 is 3x, and it is equals to 10 over 2, that is 5. So in total, we found out that 3x equals to 5. Here we divided this equation by 3, and found out that the radius x equals to 5 thirds. Again, in total, we found out the radius x of the circle equals to 5 thirds units inside. Our task is to find out the area of this circle. We know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared must be equal to x squared. So in total, the area of our circle must be equal to pi x squared. But x is 5 thirds, then therefore x squared must be equal to 5 thirds squared. So in total, the area of our circle must be equal to pi times 5 thirds squared. So it is pi times 5 thirds squared. 5 thirds squared equals to 5 squared, that is 25, over 3 squared, that is 9. So in total, we found out that the area that we are looking for this question, that is the area of this circle. In total, it is equal to either 25 pi over 9 square units in size. So in terms of numbers, the area of this circle equals to 8.73 square units in size. Okay, thank you very much.